Okay, class, we're coming back to cover goal 2, using rational functions in real life. And in the last example, example 4, we're on page 549. So let's read at the top together. It says, manufacturers often want to package their products in a way that uses the least amount of packaging material. Finding the most efficient packaging sometimes involves finding a local minimum of a rational function. All right, so this is one of these examples where that's similar to kind of like that box example that we did, where you're trying to use the smallest amount of box in order to give you the biggest volume. This is similar in the sense that we're trying to figure out the least amount of surface area that gives us, like, I think, the most volume. And so let's just read this together. It says a standard beverage can has a volume of 355 cubic centimeters. So the volume is standard is, metric system, they're saying is 355 centimeters cubed. Oops, centimeters cubed. All right, so it says find the dimensions of the can that has this volume and uses the least amount of material possible. Compare your result, the dimensions of an actual beverage can, which has a radius of 3.1 centimeters and a height of 11.1 centimeters. Okay, the first thing they're telling us to do is they're saying, okay, well, the volume of a can is this, pi r squared h. And they want us to solve this in terms of h, because we're going to use that in the surface area formula, which is surface area equals 2 pi r squared plus 2 pi h. I don't know if you remember this, like toward the end of last year when we did the surface area of a cylinder. That's what this is. It's we think about a cylinder, right? And we're talking about this the surface area is like if I were to cut this whole thing open and lay it flat, this would be the surface area. So I've got two circles here, right? And then I've got the rectangle that this would be if I cut this down the middle and laid it flat. I'd have a rectangle that would be, that would have the circumference of the can here as this dimension and the height here. So if this is r, remember the area of a circle is pi r squared, but I got two of those, so that's what this is. This is the area of these two circles. And then this is the rectangle. Right here is what this is. So this is, oh, I forgot the r, didn't I? 2 pi r h. Yeah, 2 pi r h. So this is 2 pi r right here. And this dimension is h. And so that's where that comes from. All right, so they're saying first thing we're going to do is we're going to solve for h, and then we're going to take and represent the surface area in terms of h as well. We're going to put that in. So if I solve for h here, h is going to end up equaling the volume, right, divided by pi r squared. And so now we're going to take this h and we're going to pop it into the surface area formula. So we got surface area equals 2 pi r squared plus 2 pi r times h. But what is h now? It's the volume, right, divided by, and in fact, they're actually using the actual volume of 355. So it's really 355 over pi r squared. All right, now we're just going to do a little bit of cleaning up here on this side, and we're going to end up with S, surface area, equals 2 pi r squared. And then I can take and cancel out an r here, right? And I'm going to say 2 times 355, and that's going to, and also I get the pi's go out, right? So I'm going to get 2 times 355, well, that's 710. And then I just am left with r. Okay, so there's our surface area. All right, so in essence, what you're going to do now is you're going to graph this rational function in your calculator, and you're going to find the minimum value. We're looking for the minimum value of s. We're trying to find out what r is for the smallest value of s. So you're going to put this in your calculator as y equals 2 pi r squared plus, and you got to put this in parentheses, 710 divided by, oh, and actually this will be x here, and that'll be x. So put that in your calculator, And then also, I'm just to save you a little bit of time, I'm going to give you the window dimensions. So, and again, it's trial and error, and I'm sure you could figure it out. It's just going to take takes a little bit of time. So the X-Men, we're not going to be dealing right with X is representing the radius. We're not going to be dealing with any negative radii, right? X max, it certainly is not going to be more than 10 centimeters, okay? And then the X scale is going to be equal to 1. And then the Y min, same thing. The surface, Y is representing the surface area here. We're not going to have any negative surface area. And then the Y max, I chose 500 so that you could see enough of the graph. And then Y scale is 50, I think you can do 50. Okay, and then let's see if that works. Let me see. Yeah, and okay, so put that in your calculator. 2 pi x squared plus parentheses 710 divided by x, and then hit graph. Okay, now I want you should see something kind of similar to the picture that you see in the book. And notice that, I mean, this is a rational function. It does have hyperbola, but we're only looking at one aspect of it. We're looking at the positive hyperbola, that branch. And I want you to find the minimum value. So remember, second calc minimum, option 3. And you're going to pick the left bound. So you want to be left. You want to get your cursor to the left of the lowest dip there. Press enter. You want to go off to the right of the lowest amount, and then for the guess you want to try to get on top of where you think the lowest part of the graph is, and press enter, and you should get x equals 3.83, something like that, so 3.8, and then y equals 277, and they're saying 0.54 in the book, yeah, and this says 2.83. 72. They took a few more numbers here. But you should be able to get those values. So what is that telling us? That's telling us that if the radius of the can is 3.8, roughly, centimeters, that it would take a surface area of 277.54 I guess centimeters squared, okay, for surface area. So the can would be 3.8. Now let's look at the regular can. They said it's 3.1, and you can look at the two diagrams, because then if we go back in, we can put this 3.8 in and actually figure out. I think we can figure out what h is right here, because we can put the radius in here. And we got the volume, right? And we can calculate what h is. And what it turns out to be is like a really short, fat can would give us the smallest amount of surface area that would still hold that volume of 355 cubic centimeters. The can to the right, is what we're more accustomed to. It takes more surface area, though, to create that can. And the book is actually sort of analyzing. They're kind of, the other can would be harder to hold, right, because it's so much wider than the other can. But it could minimize the amount of surface area in terms of materials that it would take to manufacture that can. All right, that is it for 9.3.